Mankind has always cooked food using everything from campfires and barbecues to gas and electric stovetops. Now he can use an induction cooktop. It doesn't need a fire, a flame, or a red-hot burner. It uses innovative cooking technology our ancestors never dreamt possible and would swear was pure magic. An induction cooktop doesn't use traditional cooking elements above or below the cooking surface. It uses copper induction coils that generate high-frequency electromagnetic fields. These fields excite the molecules in the pan, creating heat only in the cookware itself. That's why the yolk remains cold, and only what touches the pan cooks. The magic starts with the punching press that stamps computer-generated shapes into sheets of cold-rolled steel. These cutouts fix the position of the induction coils that sit under the glass surface. A press brake bends the four sides of the steel so it will hold a glass ceramic top in place. In the meantime, a machine spray paints the burner box, the visible part of the cooktop. A technician affixes the labels and the power cord onto a housing box that will conceal the induction electronics and coils. She secures the power cord for strain relief. She then attaches the power cord ground and the system ground wire to the housing box. She places a cover on the box and screws it into place. Another technician puts together the induction electronics. These assemblies of circuit boards, cooling fans, and semiconductors drive the cooktop. She covers the electronics with insulation and a metal carrier plate that will support the induction coils. Then she feeds the user interface wires through the top of the coil carrier plate. The technician screws the carrier plate and the electronic assemblies together, then grounds the electronics. Protective tape around the openings will prevent the user interface wires from rubbing against the coil carrier plate. And some insulation will protect the electronic assemblies. She closes that side of the electronic housing box and attaches all the power cables. A sheet of insulation goes on the flip side of the box, where she mounts the electromagnetic coil assemblies. The iron slugs on the back of each coil pod help distribute the electromagnetic energy to the cookware evenly. She connects the coil assembly to the system board. Then she places the remaining 4 coil assemblies onto the carrier plate and connects their leads to the system board. Meanwhile, another technician assembles the components of a glass touch user interface panel. She connects the interface to the steel holder that was bent into shape at the start and is now attached to the black burner box. She covers the cooking surface and control panel with an attractive stainless steel frame, then connects the system board to the control panel. She closes up the other side of the burner box. Then she bolts everything down to complete the cooktop. A technician tests the unit. Using a metal object to activate the electromagnetic field, he verifies that the controls respond properly. He makes sure all 5 induction coils are working and the power output from each coil is correct. The control panel confirms it's a success. Clean, safe, and energy efficient, induction cooktops make cooking food quick and easy.
A quality pot or pan has the ability to heat uniformly throughout so that food cooks evenly. Copper is by far the best heat conductor, but copper cookware is very expensive. Aluminum conducts heat well but isn't durable, so many cooks use stainless steel cookware that contains aluminum. This high-end line of stainless steel cookware has an aluminum core running throughout. Production begins with 2 stainless steel sheets. Using a spot welder, workers tack them together along one side. Then they lay the connected sheets onto an assembly fixture. A vacuum arm pulls up the top sheet, and they insert an aluminum sheet in between. This metal sandwich goes onto a conveyor that takes it on a 10-minute ride through an oven. The heat, 370 degrees Celsius, softens the metals. This preps them for the bonding and shaping operations to come. From the oven, the metals enter the first mill, which uses electric current to heat and bond the 3 layers into one. Now it's into a second rolling mill. This one strengthens the bond. That steam you see is the water-soluble lubricant evaporating against the hot metal. Now the bonded metal travels to a second oven for reheating. This further strengthens the bond. From there, it's into a 100-ton press. It forces down a die to cut out the starting shape of the piece of cookware they're making. They clean off any debris from the metal cutting. Even a minute shard getting under the press would damage the metal. Now the disc goes into a 200-ton press containing a forming tool, which forms it into the shape of a 25-centimeter frying pan. A sheet of paper between each shaped pan prevents scratches. They install different forming tools on the press to produce different types of cookware, from saucepans to stock pots. Now that they've formed the shape, they need to do some refining. This trimming press first removes excess metal around the perimeter. Next comes what they call edge conditioning. The perimeter trimming left the rim rough, so they now smooth it by running it against a cutter at high speed. The next stop is a polishing machine with an abrasive belt. The pan's interior surface rotates at high speed against the belt. The result is a high-gloss finish. Now for the exterior. The pans go onto a rotary buffer. Each pan runs against 10 progressively finer buffing wheels. By the end of the circuit, the stainless steel has a mirror finish. It's time to get a handle on this cookware. First, they use a press that's essentially an industrial-strength hole puncher. It applies some 18 tons of force to perforate the metal. Workers position rivets in the holes, then use another press to squeeze them flat. As the rivets spread outward, they secure the handle firmly in place. This company's top-of-the-line stainless steel cookware contains a copper core within the aluminum core, a structure designed specifically for induction cooking, the latest culinary technology. A thin cut along the perimeter exposes the copper within, giving this high-end cookware a signature look. After all, performance and style are everything in an industry where the competition's always heating up. When the pressure is on, the juices start flowing for quick results. The pressure cooker traps steam inside to raise the cooking temperature and produce a meal in minutes. The technology has been around for centuries, but was only adapted for household use in the 1930s, when the concept really picked up steam. Modern pressure cookers have new lid-locking technology and safety features, keeping it on the front burner in the kitchen gadget department. A pressure cooker starts with the stainless steel disc. A dip in some lubricant will aid the forming process as equipment pushes the disc over a pot-shaped die. That flat disc is now a nicely rounded pot. Next, this punch cutter moves in to make notches in the pot's rim. These notches will interlock with the pressure cooker lid, allowing it to hold up tight against steam pressure. Next, they submerge aluminum discs in a liquid mix of aluminum and silicone to give them an even coating. While the disc is still damp, they arrange it on the bottom of the pot. Then set a stainless steel disc on top of it. A turntable delivers the pot to an element that's heated to 610 degrees Celsius. This intense heat activates the aluminum and silicone solution to fuse the discs to the bottom of the pot. Then it's into a cooling tank, where the pots float towards the next station. There, two blades shave away the ragged edges of the fused layers on the bottom of the pot. This creates a cosmetic beveled effect. That layer of aluminum sandwiched between the steel will improve the pot's heat conductivity. And now it's time for some grit and polish. In this special chamber, sanding and buffing tools add luster to the pots. The pressure cooker pot then takes a trip through a washing station to clean off the sanding residue. And now it's ready for the crowning touch, the lid. It takes 6 pressing operations to shape it completely. The holes at the center are for the pressure cooker's 2 safety valves. To install the main valve, they align a retaining ring with the lid's larger hole, then pop the spring valve into that hole. An automated device underneath tightly screws it into place. The backup valve goes in the smaller hole. These 2 valves are crucial. They'll release excess steam to avert an explosion. A rubber ring creates an airtight seal with the pot. They test the valves and check the sealing ring, along with the lid's closing mechanism. This plastic cooking guide encircles the main safety valve, but doesn't impede its function. They weld several bolts into the pot on either side. They leave a bit of space between the bolt heads and the pot. This allows them to install the brackets for the handles. They torque the bolts to tightly secure the bracketed handles. After all, a pressure cooker is one thing you don't want to lose your grip on. And now this pressure cooker is in the home stretch. There's one last test, which they perform on randomly selected pots. They pump the pot full of air to simulate the effect of steam and confirm that this pot can handle the pressure. Pressure cookers with double walls are another innovation. They'll keep that stew warm longer to ease the pressure on the chef.
Any good cook knows that you're only as good as your tools, so using the right kitchen knife for the job is essential. From chef's knives and cleavers to boning knives, filleting knives, and paring knives, a serious cook buys only quality cutting utensils and stores them in a block to keep their blades sharp. Today's blades are truly a cut above the stone tools the cavemen used. Knife making is now a science, producing tools that really give you that edge in the kitchen. First, they roll out steel by the sheet from a big coil. Then, this machine called a press cuts out the blades with a punch, and it really does pack a punch. It presses down with 110 tons of pressure in order to make these steel cutouts. Next, things get really hot. They roll baskets full of the blade cutouts into a high-temperature furnace. The blades bake at almost 1,600 degrees Fahrenheit for 2 hours. This hardens the steel. Out of the fire and into the freezer, the blades chill out at sub-zero temperatures, negative 56 degrees Fahrenheit for 2 hours. This freezer is cooled by liquid nitrogen. Now we have what they call cold, hard steel. Next, they douse each blade with water while a belt grinder smooths the back of the blade and sparks fly. Continuous water keeps the steel cool and hard, while a sander smooths the back of the blade. Now a robot moves in. This robotic arm has vacuum grippers like an octopus. It picks up a blade by suctioning. Then it transports it to a grinding machine. The machine grinds the blade to give it that cutting edge. Water flows continuously through the grinder again to keep the steel cool. The robot keeps everything moving, putting a paring blade through the grinder every 12 seconds. The automated process for this bigger blade is a bit different. This robotic arm holds the blade in a grip, rather than through fast-action suctioning. That's because it takes more time to grind this big blade called a cook's knife. So this arm holds onto this blade a few seconds longer. But if this makes you nervous, relax. The robot doesn't have a habit of dropping them. Some blades require a personal touch, like this Chinese chef's knife used for chopping vegetables. The worker runs the blade over the grinding stone very carefully. This gives it a very thin edge. Then a laser burns the brand name onto the side of the blade. Next, a piece of wood goes into a clamp, and a router shaves it into the shape of a handle. The end of the blade now fits neatly into the handle. A worker clamps the knife onto a riveting machine. Those things that look like bullets on an ammunition belt are actually the rivets. The machine forces the rivets into the handle from both sides. The rivets lock together inside the handle, so they can never be taken apart. Now they grind down any protruding steel from the handle. This makes the wood flush with the steel from the blade. The piece of metal that extends into the handle is called the tang. It gives the knife weight and balance. Finally, they hone the knife between two stone grinding wheels. With this kind of an edge, these knives will slice paper. But these knives will do their best work on the cutting board, where they'll make the cook's life easier and meals tastier, no matter how you slice it. Cast iron stoves have been adding warmth to people's lives for more than 3 centuries. Today, there are new reasons to cozy up to this invention. It's had a major update. Modern stoves burn wood more cleanly and efficiently, providing heat without the dirty fallout from the chimney. Modern cast iron stoves hardly resemble their smoke-belching, soot-spewing predecessors. The design creates a hotter fire, so it requires less fuel and releases little smoke. It all starts with a pile of iron scrap. Things like old stoves, sinks, brake drums, and rotors. A magnetized crane transfers the scrap to a propane-fired preheater. 12 minutes spent in the preheater removes moisture from the iron scrap. The scrap iron spills into a hopper that funnels it into an electric furnace. The temperature in the furnace is a blistering 2,700 degrees Fahrenheit, and the iron melts into a fiery liquid. The furnace tilts to pour the molten iron into a ladle for transfer. Next, they make the molds of the stove parts, using a mix of sand, clay, water, and coal. They blow the ingredients between the aluminum patterns. A hydraulic system squeezes the patterns together. The sand mix compacts and takes the shape of the patterns. They now have sand molds. The molten iron arrives and flows into a channel leading to the molds. As the liquid metal cools, it solidifies into the shape of the mold. A vibrating conveyor shakes and breaks the sand molds to reveal the cast iron stove parts. A worker knocks off unwanted bits, and then it's into a blast cleaner. Inside the blast cleaner, steel grit bombards the stove parts to remove remnants of the sand molds and expose the metal. Essentially, it blasts the dirt off and they come out clean. An employee grinds the edges of the metal stove parts. He blends in the line created where the two parts of the mold came together during casting. It takes 40 parts to make one wood-burning stove, and each one is cast in a sand mold made from a pattern. Next, a worker drills threads for the bolts that will hold all the parts of the stove together. Once the surface of the parts has been prepped, they spray an enamel coating onto them and bake it on. A laser then cuts out a steel heat shield for the back of the wood stove. The intricate cuts are computer-driven. An employee bends the heat shield to fit the stove. Next, a worker packs a kind of mortar into a silicone mold of the firebox. The table it's on vibrates to settle the material and eliminate air pockets, so the firebox will be able to withstand high temperatures. The shape of the firebox is crucial to the stove's energy efficiency, and so are the holes that have been molded into it. These strategically located holes will introduce fresh air to burn off gases that would otherwise go up in smoke, preventing energy loss and pollution at the same time. The parts have all been fabricated, and they're ready to put the pieces together. They assemble the stove from the bottom up. They bolt the parts and seal the joints to make them airtight. The assembly takes about an hour. This cast iron stove is now ready to keep these fires burning for many years to come. A cylinder stove is designed for campers who like their creature comforts. Just pitch the tent and set up the stove inside. It keeps things warm and toasty for most of the night. It also has a cooking surface and a tank at the side to provide hot water for washing. No need to huddle around a campfire to stay warm. A cylinder stove can take the chill out of the wilderness experience. The cylindrical shape means it can take the heat. It will expand and contract with the temperature change and still maintain its original shape. The cylindrical firebox starts with a flat sheet of steel. A worker feeds it through a roller repeatedly until it reaches the desired shape. Then a plasma cutter cuts an opening for the stove door in another sheet of steel, following a pattern overhead. The plasma cutter works by sending an electric arc through compressed air, and the result is a clean cut. He now places the stove body on the door framework and clamps the assembly in a special jig to secure it as he welds the two parts together. He then places the back plate on the workbench and positions the other end of the cylinder on it. He clamps them there and welds them together. Using the plasma cutter, he trims the front and back of the stove. The trimming rounds the ends nicely. From 3 flat sheets of steel to a cylindrical firebox, the transformation has taken less than 10 minutes. The welder now reinforces the underside of the stovetop with several braces, arranged in a grid pattern. This extensive bracing will prevent warping to keep the stovetop perfectly flat under the intense heat of the wood fire below. This is the stovetop before and after bracing. After cutting a hole for the stovepipe, he inserts a piece of pipe temporarily so that he can correctly install a stovepipe collar. Once the collar is solidly attached to the cooktop, he removes the stovepipe. He then bends the rim of the collar in 4 places, creating tabs to keep the stovepipe from sliding into the firebox. He's now ready to join the cylindrical firebox to the stovetop. He locks them in position and welds the entire assembly. This final welded seam seals the stove for an airtight and long-lasting burn. Next, he positions leg fittings on the belly of the stove, using a sawhorse-style tool. Once he welds the fittings to the stove, he removes the tool. Then it's over to a computerized plasma cutter. It cuts damper holes in the stove door. Damper holes are used to regulate the flow of air to the fire. They also install a baffle plate on the back of the stove door to keep sparks from flying out into the tent. The worker attaches the door to the stove with a hinge. He tests it to confirm that it opens and closes easily. Another worker now rolls pipe for the chimney, using galvanized steel because it doesn't rust. He interlocks the seam and flattens it. He crimps the ends to connect the pipe to the other pieces of pipe. There are 5 pieces of stovepipe in all, and they can be stacked together for transport. With the latch now attached to the stove door, he sprays black stove paint onto the cylindrical firebox. The paint job will prevent rusting. Finally, he rivets a brass manufacturer's tag onto the stove front. Now it's time to pack it up. From the grate to the water tank to the stovepipe, everything can be stowed inside the firebox, making it completely portable. Assembly in the tent should take about 5 minutes, a small job for a long-lasting burn. The biggest cylinder stoves are designed to hold a fire for an entire night. And with the proper setup, campers should sleep safe and sound. Installing a piece of heat-resistant rubber protects the tent around the stovepipe. Then it's time to hunker down for the night and enjoy a little warmth in the wilderness.
Wooden utensils may date back to prehistoric times, yet today they're a popular cutlery option for the modern dinner table. Typically a high-end product handcrafted by artisans, wooden forks, knives, and spoons appeal to people who are drawn to the organic beauty and warmth of wood. Traditional in material but modern in design, each of these wooden utensils is meticulously handcrafted from a single piece of maple. Maple is dense, so it doesn't develop cracks, which can harbor bacteria. It takes up to 28 steps to make a utensil. First, they plane a maple plank to a specific thickness. Then they cut it into blocks the length of the utensil, in this case, a fork. They place each block on a curved template and trace the curve, which matches the arc of the fork's handle. With a bandsaw, they cut along the trace line. The center of the curve runs parallel to the grain of the wood. This makes the handle and tines of the fork stronger than if the curve would run perpendicular to the grain. They clamp the block to another template and profile the curve on a machine called a wood molder. Then, with the bandsaw, following the curve, they cut the block into 8 mm thick strips. The curve is quite pronounced to give the fork an elegant line. They clamp up to 10 strips at a time onto this woodworking machine. Then they start her up. Routers descend and, guided by computer software, simultaneously carve the strips into forks. After 7 minutes, each curved strip, while nowhere near the finished shape, does have a defined handle and 4 tines. A strong squeeze snaps off the excess wood. Only small nubs of excess wood remain, which they now remove by running the fork against a sanding belt. From this point on comes finer detail work that can be done only by hand. Starting on a balloon sander, they add or release air, adjusting the inflation pressure to produce a soft surface against which to sand a curved utensil, and a hard surface against which to sand a flat one. Once they've refined the back of the fork, they manually sand the areas that motorized sanders can't reach, first beveling the tines to sharp points, then sanding in between the tines. It's important to keep the tines thick so they won't wear out with use. Next, they sand the entire fork with a fine grit sandpaper to remove any faint ridges left by the balloon sander. They finish with an ultra-fine sanding to make the fork feel silky smooth. Now that the fork has its final shape, they stamp the company's logo into each handle. They inspect each fork under 8 times magnification, paying special attention to the points of the tines. To ensure the top of the fork remains smooth, they soak it in hot water. This draws up the wood's short fibers, so they can then be sanded down. The final step is an intricate hand-applied finishing process. 3 coats of a proprietary mixture of food-safe plant oils, waxes, and lemon. Lemon works like a solvent, diluting the mixture so that it penetrates deep into the pores of the wood. After the last coat dries, they manually polish the surface with an ultrafine abrasive pad, sweep off any wood dust, then let the finish cure for 28 days. The finish brings out the grain and color of the wood. It also protects against food stains, abrasion, and moisture over the lifetime of the utensil. Wooden cutlery doesn't just look different, it sounds different. No ting of metal utensils on dishes as you eat. When dining a la wood, the only thing you'll hear is conversation.
Food just slides off nonstick cookware's remarkably slippery surface. In 1938, an American chemist was experimenting with refrigeration gases. A waxy substance formed. Years later, when bonded to cookware, it gained a nonstick reputation. When it's time to fry, using a nonstick pan averts a messy situation. The nonstick coating is one of the slipperiest solid materials on Earth. Called polytetrafluoroethylene, the name is a bit of a mouthful, but the appeal is simple. Food won't get stuck on this non-stick surface. To make the aluminum pan, they use 70% raw material and 30% leftovers from prior production of pots and pans. They fire it to a molten state and filter it to remove contaminants. The liquid aluminum flows into vertical rectangular molds. A jacket of water around the molds cools the aluminum to take it from a liquid to a solid. A crane extracts the cast slabs. They're heading to a heating chamber to soften the slabs. This will allow the metal to be shaped and formed. A saw slices the slabs in two and trims the ends. More blades scrape the top and bottom to remove impurities. A conveyor repeatedly feeds the shorter slabs to heated rollers. Guides at the side maintain the width, while the rollers compress the aluminum, taking the thickness down to about 2/10 of an inch. The rolling also elongates the slab substantially. It starts out at 6.5 feet long, and after a few minutes of rolling, it's been stretched to well over 100 yards. Pizza cutter-style blades trim the edges of the aluminum sheet. Another roller winds the aluminum into a big coil. They then unwind it and squeeze the aluminum to flatten it. Machinery now pulls the long aluminum sheet forward to a 132-ton punch press. This powerful press forces the metal around a frying pan-shaped die and then punches out the shape. The freshly formed aluminum frying pan falls onto a conveyor below. The leftover aluminum will be used to make new frying pans. The pans now ride a conveyor through a washing station, where they're cleaned and then treated with sodium hydroxide. This opens the pores of the metal to allow an enamel coating to stick to the outside and the nonstick finish to adhere to the inside. A worker inspects the pans and places them upside down on spray fixtures. It's a tight fit to shield the inside from the enamel spray that comes next. The pans spin on the fixtures and twirl by the spray nozzles for an even application of enamel to the exterior of the pans. A clear glossy coat follows. The frying pans transfer to a dryer conveyor. The hot air pulls out water from the enamel coating, and the color goes from gray to chalky white. An automated squeegee silk screens the company's name and other information onto the pan bottoms. They now enter a long curing oven heated to 1,040 degrees Fahrenheit. The cure toughens the enamel, deepens the color so it turns gray again, and it adds gloss. A suctioning device picks up the pan and turns it around for the inside coatings. A sprayer applies a special primer that will make the nonstick coating adhere to the pan. It then applies the nonstick coating. The pans receive 2 layers of this non-stick synthetic substance. The suctioning device releases the pan and it lands upside down. Then the pans journey through the oven again to cure the non-stick finish at around 800 degrees Fahrenheit. On exit, water rains down to cool the pans and rinse off any contaminants. Then they go through an infrared light chamber to dry off. From a plain shell to a pan with an enamel finish on the outside and a non-stick coating on the inside, the transformation has taken just 1 hour. A worker now aims a laser and aligns it with lettering on the bottom, allowing him to punch holes in a precise location on the side of the pan. He slides pins into the holes and slots them through holes in the handle fitting. Using a ram, he flattens the pins to rivet the handle to the pan. Now, no matter what's cooking, cleanup should go smoothly.
Frying pans have been around since ancient Greece and Rome. These wide and shallow pans can be used to sauté, sear, and scramble food. Water released from the food during cooking causes that sizzling sound. The steam dissipates due to the shape of the pan, allowing the food to cook crisply. A good non-stick frying pan is a must in the kitchen. A frying pan can be made of any heat-conductive metal, in this case, aluminum alloy ingots. They melt the ingots. A robotic ladle scoops up the molten aluminum and transfers it for casting. They'll use this two-part die to transform the liquid aluminum into the shape of a frying pan. The die closes. The robotic ladle pours the liquid aluminum into the die through a cylindrical port. A piston forces the aluminum into the die. This high-pressure casting produces a very precise shape. After about a minute, the operator extracts it. Using computerized tooling, they cut off the excess and trim the rim. The table moves to meet the tool as it cuts the edge of the pan to specifications. A worker grinds off any remaining unwanted bits. She also rounds the rim of the pan a little more. They cast the pans in several sizes and thicknesses for different frying pan models. An employee keeps a detailed inventory of the pans in order to plan the next stages of production. Next, it's into a sandblasting chamber. The sandblaster cleans off oil and cleaning residue. It also roughs up the surface of the pans to prepare them for coating. An employee scrubs off the sand using an abrasive pad. The pans twirl on a pod as a plasma flame melts 3 different powders onto them to give them a ceramic coating. The coating will protect the pan from corrosion. An employee scrubs each pan with an abrasive pad to remove the residue. On to more pods now. The frying pans revolve a little more slowly this time as torches heat them to a temperature of approximately 80 degrees Celsius. This preheat preps the pans to receive the final coatings. They prepare up to 5 proprietary coating formulations for each frying pan model. Each one contains dozens of chemicals and hundreds of thousands of tiny diamond particles. The diamonds will increase durability and heat conductivity and make food less likely to stick to the surface of the pan. For the final coating, they blend in the non-stick chemical known as PTFE. They spray the different coatings onto the surface. The spinning ensures even coverage, as the coatings melt a bit onto the hot pans and adhere. The second to last layer is a primer. It allows the final non-stick coating to bond to the frying pan. At the end of the line, an employee inspects the finish and sprays a little more of the non-stick formulation onto the handle fitting. The frying pans then ride a conveyor through a 12-meter-long furnace to bake the coatings onto the pans. An employee checks the finish for bubbles, scratches, or color inconsistencies. Once the pans have cooled, a robot transfers them to a lathe. The lathe spins the pan as a tool shaves off a thin layer of aluminum, creating a clean, level surface on the bottom of the pan. A suctioning robot moves the frying pan to the next station, where a human positions a handle on a fitting on the pan. An automatic screwdriver secures it. Now it's over to a test station. The technician heats one of the frying pans on a cooktop and activates a mechanical arm with an abrasive pad. It rubs the pan thousands of times with a coarse piece of sandpaper like this one. If it doesn't scratch the pan, the entire production run is approved, and thousands of non-stick frying pans are ready to leave the factory. It's time to turn up the heat.
There are several different ways to manufacture aluminum pots and pans. Some factories have giant machines that simply stamp out or mold the cookware, while other factories use a technique called metal spinning. To make cookware that's safe for food use, the aluminum must be pure, no other metals mixed in. It all starts with a round aluminum sheet called a blank. They stamp the pot size and the company name on what will be the bottom of the pot. They clamp it onto a lathe, centered against what's called the chuck, a metal mold shaped like the inside of the pot they're going to spin. The lathe spins at 2,000 revolutions per minute. Guided by computer software, the spinning tool, a round wheel made of special plastic, pushes against the chuck, stretching and shaping the aluminum blank, much the way potters stretch and shape clay against their hand on a pottery wheel. Except that metal spinning works sideways, not up and down like pottery. The machine trims off excess aluminum as it rounds the edges. The factory has no use for these very sharp metal leftovers, but it doesn't throw them out. Aluminum is difficult to mine and therefore very expensive. So scrap aluminum is sent off to be recycled into other products. After the final trim to the finished size, another trimmer moves in to take the sharpness off the edge. It's taken 4 minutes to spin this 8.5-gallon pot. Now it comes off the lathe. They punch out handle holes. Then rivet on aluminum handles. The pot is now finished. Items that aren't as large and heavy are spun on a hand lathe. This is where you need an experienced metal spinner. Because this trade isn't a mechanical science, you've got to have a feel for it. Besides cookware, many other aluminum products are spun on a lathe. This is a light reflector, that round aluminum fixture that covers light bulbs in factories, stores, and arenas. When working the hand lathe, the metal spinner uses what's called a scissor tool. It's the equivalent of the plastic wheel on the automated lathe. As the blank spins, he moves his tool further and further down to stretch the aluminum into the right shape. This is a sausage funnel. And this will be the inside tube of a cake pan. He makes the body of the cake pan on a different lathe, using a variety of tools to get a variety of effects. This beading tool creates an edge, for example. Almost all metals can be spun, though some are better suited for the technique than others. Aluminum and steel are very formable metals, so they provide the best results. Pyrex is an idea cooked up by the wife of a glass industry scientist in 1913. She believed the tough glass used in lantern globes would be great for baking cakes in. So she baked one in some glass her husband brought home. The cake was a hit. changing the notion that glass was too fragile for the oven. Today in most homes, you'll find different types of cookware, many of which are made from Pyrex. To produce some dishes, a batch feeder pushes ingredients into a big furnace as they spill out of a bin overhead. Silica sand is the biggest part of the mix. It's a crystalline substance and it makes glass transparent. The batch also includes soda ash and recycled glass. Some of the other ingredients are a trade secret. The furnace heats the mix to the melting point, over 2,700 degrees Fahrenheit. It turns into molten glass that looks like lava. The glass in this lava-like form will spend up to 24 hours in the furnace. On its way out, mechanical shears cut it into gobs. The gobs slide down a water-cooled chute and drop into a baking dish-shaped mold. There are 16 molds on a rotating table. As it turns, the table delivers the gob-filled molds to a plunger, which presses them into the baking dish shape. Continuing to rotate, the table positions the molds under blowers. They cool the freshly molded glass so it holds its shape. A mechanical arm suctions up the glass dish and sets it down on another revolving table. Flames lick the glassware from burners above and below. The dish is exposed to a temperature of over 1,800 degrees Fahrenheit. This softens its sharp edges so that the rim is smooth. Next, hoses blast high-pressure air, cooling the dishes to solidify them, so that a mechanical arm can pick them up without ruining them. It transports the glass dishes to a conveyor belt. Further down, another arm feeds the dishes to a kiln, where heating and cooling cycles temper the glass. This is what gives Pyrex its strength. Now it's time to make the lid. A different plunger presses glass gobs into a lid shape. Every lid needs a knob, so a valve inside the mold forms it and then thrusts the lid up to be picked up by a mechanical arm. The arm flips its lid and sets it down on a conveyor belt. The lids are on the move, traveling through a tempering kiln. On their way out, a fan cools them off so that they can be handled by human hands this time. Workers inspect each glass lid before packing them. On another line, measuring cups are produced. Little platforms lift the measuring cups to suctioning arms that protrude from a revolving silkscreen machine. A little squeegee forces enamel through a screen, printing measurements onto the cup. Over in the lab, a worker roughs up a sample dish. By rubbing it with sandpaper, he mimics years of wear and tear. But it's about to be subjected to even more abuse. He places a sharp tool in the center of the dish and takes aim with a hammer. Will it break without shattering into numerous little shards? It's a clean break, which means this dish has met the quality standards.
A Bundt pan is for baking a dense, ring-shaped cake called a bundt. It typically has a fluted or swirled design. It originated in Europe hundreds of years ago and quite possibly gets its name from the German Buntkuchen, Kuchen meaning cake and Bundt meaning a gathering of people. Bundt pans were originally ceramic, which is fragile, or cast iron, which is heavy. Today's version is typically made of cast aluminum, unbreakable and infinitely lighter. It also has a non-stick coating. At the factory, they begin the production process by melting ingots of recycled aluminum. The furnace heats the ingots to 700 degrees Celsius, at which point they liquefy in about a minute. From the melting furnace, workers transfer the molten aluminum to a holding furnace, which keeps it in a liquid state until casting. The casting process is entirely automated. A ladle descends into the holding furnace and scoops up just under 1 kilogram of aluminum, enough to make 1 Bundt pan. The ladle then pours the molten metal into a sleeve, which a high-speed ram immediately pushes into a steel Bundt pan mold. The pressure and speed combined shoot the molten aluminum into every nook and cranny of the mold cavity. As the hot aluminum hits the cooler mold, it solidifies in about 10 seconds. Then the two halves of the mold automatically separate, and a robotic arm extracts the cast pan. Between castings, a robot cleans the mold with a blast of air, water, and lubricant. This removes any aluminum residue, leaving the mold surface pristine. This is critical because even a tiny speck of dust left behind would mar the next casting. As each pan comes off the machine, workers inspect it for any casting flaws. When it comes time to produce a different style Bundt pan, like this one with 6 mini cake forms, they simply mount the corresponding mold onto the casting machine. As the machine fills the mold under pressure, some aluminum oozes out between the two halves of the mold. Now a worker cuts off that excess with a single strike of a trim press. The scrap pieces go back into the furnace to be remelted. Next, a computer-guided router, working 2 pans at a time, smooths the rough edges. Then it refines the handle slots, finalizing the shape. The aluminum surface must be pristine for the non-stick coating to adhere properly, so the pans now go through an industrial washing machine. 1 wash and 3 rinse cycles, and then, before exiting, a drying cycle. Workers put the pans upside down on fixtures, which travel down the exterior coating line. As the pan spins by, spray guns apply a silicone-based decorative coating to the outside surface. The pans then travel through an oven for 15 minutes to cure the coating. Then workers flip the pans right side up and place them on fixtures which spin them through another spray line, this time to coat the inside. The interior coating is a food-safe silicone polyester material designed to release the cake easily from the pan. It's similar to a non-stick coating on a fry pan, the difference being that the chemical composition is designed to prevent sugar rather than protein from sticking. Again, the pans go through an oven for 15 minutes to cure the coating. Once the finished pans exit the oven, workers inspect them thoroughly, checking for any flaws in the coatings. From a practical perspective, a Bundt pan's ringed shape has definite advantages over an ordinary baking pan. The tube in the middle funnels heat to the center of the cake batter, helping it bake quicker and more thoroughly. From a decorative perspective, when you compare an ordinary pan to an elegant Bundt, the latter certainly takes the cake.
Wood-burning stoves do more than create a cozy ambiance. They're also powerful enough to heat an entire house. More and more people are installing a wood stove as an additional heat source in their home. It's economical, and the new low-emission models are more environmentally friendly. Every wood stove has a fire baffle, a stainless steel barrier above the burning wood that shields the top from the intense heat. The baffle also slows down the smoke exiting by the chimney, which reduces the upward draft that the rising heat creates. Production begins with large steel sheets that are 1/4 of an inch thick. A computer-guided laser cuts out pieces that workers will shape into the various parts of the stove. The laser slices through the metal quickly and with extreme precision. And because it cuts with intense light rather than punching force, the pieces have neat, smooth edges. Workers use a strong magnet to lift and transfer the pieces to the next production area. The largest piece becomes the surround, the part that forms the sides and back of the wood stove. Workers use a machine called a press brake to shape it. A computer guides this large hydraulic press to bend the flat steel in exactly the right spots. Now they position the surround in an assembly jig to keep it steady during welding. After welding the front of the stove to the surround, they weld the air intake, which allows oxygen to enter the stove to feed the fire. Next, they weld the top, the fire baffle, and air channels near the top, which are also designed to feed the fire with oxygen. The quality of welding in a wood stove is critical because the joints have to be able to withstand extreme heat. Now they weld the bottom of the stove. It has a hole in the middle through which you sweep the embers to an ash pan below. Now they weld the flue collar, the steel ring that attaches the stove to the flue pipe that leads to the chimney. Workers now bolt the stove to a pedestal. The pedestal is also made of welded steel. Meanwhile, the door takes shape. They glue a fiberglass rope to the perimeter of the door frame, using a silicone-based glue that's resistant to extreme temperatures. This cord prevents air from seeping in through the door and fueling the fire out of control. After installing the locking door handle, they weld the door hinges. The stove's interior, where the wood burns, is known as the combustion chamber. They line it with bricks to protect the walls from warping in the intense heat. Bricks do deteriorate over time, but it's easy to replace them. The last steel part they install is the cap for the ash pan. Now, an automated conveyor transfers the stove to the paint station, where a robotic arm sprays on a coat of heat-resistant paint. Once the paint air dries, a worker removes the door to install its glass panel. This isn't your run-of-the-mill window glass. It contains ceramic, which enables it to withstand temperatures up to almost 2,000 degrees Fahrenheit. With the glass panel in place, workers can apply decorative features and information stickers. Then they put the door back on and lock it shut. They rivet on the company logo. Then install a fan in the back. The fan blows out the heat that the stove generates. When the wood-burning stove leaves the factory, its coat of paint is dry but not yet cured. The heat cures it when you fire up your stove for the first time.
Cast iron cookware is renowned for its superior ability to retain heat and diffuse it evenly. However, bare cast iron requires regular oiling to ward off rust. Not so with enameled cast iron. A glass enamel coating encases the iron, making the cookware entirely maintenance-free forever. Since 1925, this French company has been producing enameled cast iron cookware. Its high-end products are renowned for their thin walls, which makes it the most lightweight cast iron cookware available. The secret? The mineral levels in the iron recipe. At the foundry, they begin with pig iron, which has a high carbon content. Then they melt in a calculated amount of steel to further boost the carbon level. The melting oven heats the metals to 1520 degrees Celsius, liquefying them in just 45 minutes. Workers add a powdered chemical to agglomerate the natural impurities in the iron, then scoop those bonded impurities out. Meanwhile, workers mount a two-part mold template onto a machine which produces the sand molds with which they'll cast the cookware. The machine injects the sand mix into the templates. The mix contains clay, water, and proprietary ingredients which make the sand compact well. Compaction is critical because just one single grain of sand displacing from the mold would produce a flaw on the cookware. It's essential that the pouring temperature be precise and consistent, so they transfer the iron from the melting oven to a temperature maintenance oven. From there, they pour the molten metal through a mere 3 mm gap between the mold halves. The process is entirely automated because the pouring angle and speed are critical. The molten iron cools and solidifies in 20 minutes. Then the molds drop onto a vibrating mesh conveyor. The shaking releases the cast cookware from the mold, along with the metal that's solidified in the flow channels leading to the mold cavity. The cookware moves into a closed chamber where a high-pressure gun blasts the surface with steel balls to remove all remaining grains of sand. At this stage, the cookware has rough excess metal where the two parts of the mold met. So now workers smooth away these burrs using a grinding wheel on the outside and a grinding pen in the tight spots. The cookware is now ready to be prepped for enameling. A machine now blasts the entire piece with steel grits, making the surface texture uniform so the enamel will adhere evenly. The first coat of enamel is strictly to protect the cast iron and prevent it from rusting. Enamel is a form of glass. However, this enamel is engineered to be flexible because metal cookware naturally expands as it heats and contracts as it cools. After a trip through a dryer, the enamel goes into an oven at 850 degrees Celsius for about 45 minutes. During this firing, the hair-thin enamel coating becomes translucent. The second coat of enamel completely seals the porous surface. It's made of some 20 components, including enamel chips, pieces of clear glass, and pigment powders for color. An automated spray system coats the inside first. Workers wipe the edge to prevent the piece from sticking to the conveyor, then the handle because they'll paint that a different color. They spray the handle manually, then the automated system coats the rest. The iron recipe contains a high level of the mineral silicate, which helps the enamel adhere well. Once again, the cookware goes through the dryer, then into the oven at 850 degrees Celsius for about 45 minutes to vitrify the enamel. Once the cookware cools, it undergoes a final visual inspection, the last of 30 quality control checks throughout the production process. Enameled cast iron cookware lasts generations because it doesn't warp over time and remains food safe for life.
Humans have been cooking over fire with iron implements since, well, the Iron Age. Today, most outdoor cooking requires some type of appliance. And because of iron's superior ability to retain and diffuse heat evenly, a cast iron cooker is sure to get everyone fired up. This cast iron cooker may look like an ordinary barbecue, but it does so much more than grill. It also slow smokes, caramelizes, sears, and even bakes. To produce the cast iron, the company buys scrap pieces of new steel from steel mills and from factories that use steel to make their products. Manufacturers heat the steel in a preheat furnace. This evaporates any residual moisture and speeds up melting in the main furnace. The main furnace operator adds a powdered chemical that solidifies the impurities so that he can scoop them out. He also adds carbon, silicon, and other alloys to transform the steel into iron. The molds are made of a sand, clay, finely ground coal, and water mix compressed at high pressure. The molten iron causes the moisture in the mold to evaporate. The resulting steam escapes through vent holes at the top. This machine lowers the top half of the mold over the bottom half. The furnace empties the molten iron into a ladle which contains additional alloys. A worker positions the ladle over an opening at the top of the mold and pours in the molten iron. After about 2 hours, he breaks the sand mold and extracts the casting. Workers use a sledgehammer to break off excess metal. The cast iron parts are still encrusted in sand, so workers load them into a shot blasting machine. Shot blasting is like sand blasting, except instead of sand, the machine pummels the surface with tiny steel balls. The shot blasting cycle thoroughly cleans the surface. The surface is still quite rough, however, so workers refine it with hand tools, hammering off any remaining excess metal and grinding the surface smooth. The top half of the cooker has a handle on the front and half a hinge on the back. The bottom half has the other half of the hinge. A worker drills a hole through each hinge half for the shaft that will connect them. He drills holes in the firebox that will let in air to feed the fire. Using a template and laser cutter, he cuts an opening in the bottom for the ventilation draft door. He drills mounting holes around the vent and installs the draft door. Its perforated hole cover lets air in. Its solid sliding door shuts it out. The air intake feeding the fire regulates cooking temperature. The cooker sits in a handcrafted steel cart. A welder places the parts for the cart's frame in an assembly fixture which positions them correctly. After welding the frame, he files down the welds so that they'll be virtually invisible once the frame is painted. This computer-guided lathe machines the cart's cast iron wheels to the final dimensions. The sand molds used to cast the wheels were designed using century-old patterns for cast iron pulleys. Once workers have mounted the 2 wheels, the cart goes off to be painted. Then a worker installs shelves made of either stainless steel, hardwood, or composite decking planks. Workers bolt the bottom half of the cooker to the cart. Then they lower in the firebox, which holds the fuel for cooking. The recommended fuel is hardwood lump charcoal. Next, a worker mounts the cooker's temperature gauge. Then he installs the top vent. It consists of 2 cast iron discs, which rotate to let in more air or less air. Having adjustable ventilation at both the top and bottom of the cooker enables more precise temperature control. They position the top of the cooker over the bottom and mate the 2 hinge halves with the steel shaft and 2 stainless steel springs. Fiber gaskets ensure a good seal when the cooker is closed over the cast iron grates. Those grates are reversible, with one side higher than the other, providing a choice of cooking heights above the fire.